categories of generative AI hallucinations. And it's good to know them because it helps us to understand how to mitigate these hallucinations. So the first one is self-contradictions, where we have several ideas generated in single sentence sometimes that contradicts each other. Then we have a stale information coming from the model, where obviously if the model is trained on the data from previous year, you will not see there the latest information. Other is snowballing hallucinations, and they're started with some small mistake, and then that mistake goes into the context, and then from that context, more and more hallucination is snowballed on top of that. Other what we can see is a repetition of the content. So the single idea is described uh, in multiple sentences over and over. Then we have a conflicting intent, and then the reasons can be that the large language model and the overall infrastructure didn't understand what the user wanted to generate, or there were several ideas in the context that they conflict with each other, and the language model or anything on top of that were not able to distinguish the correct intent. Then we have a knowledge conflict, and it can come from the models that they do prefer their own internal parametric knowledge over the context that is presented during the RAG process, so retrieval augmented generation. Then we have a random hallucinations that can appear, can be a random words added, several characters, repeating characters, and similar things. The other can be such as the ignoring of negations. These are the famous examples where user ask to generate a sunlit beach with no elephants on them, and obviously you got pictures with beach with elephants. Other things is ignoring context or cherry picking a history of questions. So especially when we have a long context window, the model can pick only certain events or certain ideas from the context and ignore the rest. Then we have adding irrelevant information to the answers that are really not requested by the user. Then we have logical errors in the output. So the models do not possess very good logical thinking, and the underlying infrastructure around these models might not have a reliable formal logic capabilities, and that's where we see that the output is illogical with the mistakes. We can get also incomplete answers, and that can be a limitation of the platform, or they can just happen to cut the answer in the middle. Then we get a wrong format of generated text, so where a user asks for bullet points on the answers, and we'll get a long winding paragraphs and vice versa. And then we can have incorrect specificity where the user asks for a generic answer and get very concrete example, and that's obviously the user didn't want. Now, what are the root causes of generative AI hallucinations? So there are several categories, and we can broadly split them into the categories related to training data set, then a category that is related to the training of the model, and then errors and causes that comes from the uh, inference time. So the training data set can include stale, wrong, or misleading information collected from the internet. So these data sets are improving, and the creators of large language models are getting better at vetting the information that comes into these models, but still there is not everything can be checked. Then we got a training data set that has a gaps in a certain area that are important for a specific task. For example, not enough contracts for the healthcare industry, and the downstream application can suffer from that. Then we have that training data set includes data that is biased towards certain answers, even if it's not supported by statistics. And here we can have different kinds of biases. It could be a gender, nationality, race, anything what we can imagine. And this includes cases when creators of the LLMs overcompensate given bias in the opposite direction. Then we have an overfitting on certain documents that can cause regurgitation of these documents instead of expected generated text. So that has two consequences. One of them that we actually get the content of the trained the documents that were used for the training, which is not desirable. And the second one, we don't get a proper answers for our questions. We have another one, which is a reliance on unreliable shortcuts, such as events mentioned earlier in the text cause events mentioned later in the text. And that we will get really wrong answers. Then we have a cause that LLMs prefer a parametric knowledge over desirable context to generate responses. Also, we have LLMs struggle with long-term causal reasoning and often fail when the narratives are long and contain many events. And then there are the queries with multiple meanings and inability to select the correct meaning from previous queries at given context. Also, we can have a wrong recognition of change of topic in a string of questions. And we have insufficient context to correctly answer queries. So the model and the infrastructure must recognize what is necessary information to answer certain questions. We will get a wrong answers when the models try to generate some answer but doesn't have all the necessary information and it doesn't ask for it. And ability to filter out irrelevant details given in the context, and that would be especially true for a very long context window. So what is the fundamental root cause of generative AI hallucinations? So one fundamental cause is a statistical or linguistic dependencies of the next word based on given context. So here we have a sentence: an ox came down to a reedy pool too, and the model can choose, and based on the parameters, it would inside the model it would choose to drink. But our case is different, and the ox came down to reedy pool to eat, in fact. So our particular case does not follow statistical dependence. There are mitigation measures, such as forcing LLM not to rely on its internal knowledge, but only to use knowledge derived from presented context. The context window is not infinite, and its larger size creates more space for confusion. So here we have the reasons why reliable AI is a key to its widespread adoption. So unreliable AI solutions lead to high cost of validation and verification of generated results. And there is also associated cost with errors passed downstream processes and to the customers. So if we see with the red dashed line the overall total cost of the current solution, if we try to replace it with an AI solution, and if the reliability of the results of that AI solution is not good, we will get actually higher total cost. And once the reliability of the AI solution is increasing, the reliability is increasing, then the overall total cost of that AI solution is decreasing and gets better than the current solution, and that's why it's a key. So what is currently done to improve reliability of GenAI? So I think the most famous is retrieval augmented generation, RAG, and there can be many flavors of that RAG. So we can have a before generation, which is LLM augmenter and fresh prompt. We can have during generation, which is knowledge retrieval, decompose and query framework, and ever. We can have after generation, which is RAR, or high entropy word spotting and replacement. And we can have end-to-end, which is retrieval augmented generation. Also, we have self-refinement through feedback and reasoning. Here are the examples: a self-reflection methodology, minds mirror, structured comparative reasoning. And so the system is actually asking the LLM through the prompts to refine and reason based on the results. It does have its limitations, and especially where there's a mistake in the reasoning that's not captured, and it can get to a snowballing of mistakes and errors. We have very commonly used prompt tuning, which is necessary, and here are two examples: is Uprise and Sintra. These are included in many frameworks of using LLMs. It's improving the results for the downstream application up to 30%, even more. Then we have a supervised fine-tuning. Here it's knowledge injection and teacher-student approach and fine-tuning language models for factuality. That's very commonly used. Other strategies introducing new decoding strategy like context-aware decoding, decoding by contrasting layers, and inference time intervention. Then we can have introducing a faithfulness-based loss function, lost weight method, text hallucination mitigating framework, and the most important I would like to mention today is utilization of knowledge graphs. And we have several examples like factual error detection and correction with evidence retrieved from external knowledge, that's called FLEEK, and reducing hallucination in open domain dialogues with knowledge grounding, RHO. Utilization of knowledge graphs to improve reliability of generative AI. So knowledge graphs creation and maintenance requires human effort and domain knowledge that hinders scaling and usage in many fields. So what is required? So knowledge graphs need to be automatically updated to capture current knowledge. Knowledge graphs need a mechanism to infer implicit knowledge from the current content, such as missing link predictions. And the overall system must be able to capture knowledge from heterogeneous sources, such as unstructured and semi-structured documents, as well as databases. And system must be able to infer knowledge graph schema from the input data, which is very important. Otherwise, the schema creation will be very expensive. So automation of knowledge graph creation and maintenance. So here we have an example of very small knowledge graphs. And with given document, it needs to find named entities, here are the names, find the relations, create or update schema, and find the relations of the entities, and then update knowledge graph with entity or relations that are missing. So we have a short article with the legendary Martin Sheen as the head of the family. It's no surprise his children, Emilio Estevez, Ramon Estevez, Charlie Sheen, and René Estevez follow in his footsteps. His most famous son, Charlie Sheen, is passing on the torch to daughters Cassandra Estevez, Sammy Sheen, and Lola Sheen, and twin sons Bob and Max Sheen. So the system automatically infer a relation of father, son, or daughter. And here we have the relation, which is his father. Name entity recognition. So finding spans of text that constitute name entities using several prompt strategies and performing majority vote. Then tagging the entity type. We have used Wikidata hierarchy of named entity types. And then alignment with the content of the existing knowledge graph. So what we've seen in terms of cost, speed, and quality, we have utilized our instances of Llama 3.1 8B that were sufficient in terms of quality of the results, speed, and cost. We have fine-tuned the model on name entity recognition task on a custom instruct dataset. We do maintain a category of non-name entities that include numbers, dates, and general words. And also there are two LLM pipelines, single and multi-turn, to extract name entities. Then we go to extraction of valid entity relation triplets. There are three independent pathways that use LLMs to identify and extract relational triplets, such as subject, relation, object, from input data. So in this step, no knowledge graph schema is used. The triplet is accepted only if at least two pathways agree on it. The strength of the LLM is to freely extract good triplets, but the weakness is that the resulting triplets often contain redundant and ambiguous information. So what we've seen in terms of cost, speed, and quality of the findings. We have seen quality improvement by using recognized name entities during the triplet extraction process, and further improvements were achieved during downstream processing. We have compared results from GPT 3.5 Turbo, Llama 3.1 8B, GPT 4, and Mistral 7B Instruct version 02. The GPT 3.5 Turbo had the best results, but with the cost of $6 per 1,000 triplets, the cost is prohibitively expensive. The same is true for GPT-4. The reason for the high cost is there is a high number of calls to the underlying LLM in order to extract the triplet. The results coming from our local instance of Mistral 7B is sufficient with calculated 0.001 US dollars per 1,000 triplets. Entity types and relation types definitions. So we use LLMs to generate a definition for each entity type and a relation type found by triplet extraction phase. So in this case, we had a entity type as a person, and then we generate description of the entity type person, and we had a relation. In our case, would be his father. We automatically compare these definitions with an existing schema of knowledge graph if it's available and remove duplicates. The deduplicated definitions can be assessed by experts, and we have added automated regression tests. The generation of definition as well as recognition of semantically equivalent definition uses strength of LLMs. And here we have examples of duplications. So we have relation type and definition. So these are the raw data. So we have a person family name, which is a created name of a relation type, and a definition, the generated definition, the name of a person shared with other members of the family. And here, very similar one, individual last name, and the definition is the name of an individual person shared with other members of their family. And here we have person surname, a surname. A surname of a person is an individual name that he or she shares with other members of their family. So LLMs are very good at recognizing these definitions are very similar, so only single relation type will be created. Schema, self-canonicalization, and knowledge graph update. The type definitions are used to find the closest entity relation type candidates. In the case there is no equivalent counterpart in the existing schema, the type is added to the schema. The refinement phase returns back the triplet extraction step, but now using the newly updated schema. The extracted triplets are compared to the first pass of schema-less extraction, and we calculate quality scores that are used to fine-tune the extraction process. The last step is an update of a knowledge graph with newly found triplets and adding reference counts, timestamp, and document source fingerprint to each node and edge. So next in the process is a community detection performed on the knowledge graph and generation of community summaries. So here we can see the process, which is called laden, and here is a detection of the communities of the nodes that have more common with each other than with nodes from other communities. So we perform regular rounds or hierarchical clustering using laden. Laden is a community detection algorithm that can effectively discover community structures within the graph. Entities in each cluster are assigned to different communities for more in-depth analysis. A community is a group of nodes within the graph that are densely connected to each other, but sparsely connected to other dense groups in the network. Community summary generations. So these are summaries. These summaries include the main entities within the community, their relationships, and key claims. This step gives an overview of the entire dataset and provides useful contextual information for subsequent queries. So these diagrams come from the Center for Science and Technology Studies, Leiden University in Netherlands. Then we focus on a retrieval of the data from these graphs, and we have two types of retrieval processes, and one is global queries of our knowledge graph. So utilizing community summaries to conduct a comprehensive search and reason about broad questions across the entire data corpus. So each batch of community reports is divided into predefined size text chunks, and these chunks generate intermediate responses, which contain a list of information pieces known as points. Each point is assigned a numerical score indicating its importance. Then we perform ranking and filtering, and the system evaluates and sorts these intermediate responses, picking out the most critical points. These key points are then used to create aggregated intermediate responses. And the final step is final global response. The system uses the aggregated intermediate responses as context to craft the final reply. So we try to use the strengths of the large language models in terms of summarization and a strength of the knowledge graphs in terms of quality of the information. Then we have other types of queries which go for very specific answers. They are called local queries of our knowledge graph. So we conduct a localized search to reason about specific entities by exploring their related neighbors and associated concepts. User query. The system starts by receiving a user query, which can range from a simple question to a more complex request. We perform similar entity search. The system pinpoints a group of entities in the knowledge graph that are semantically related to the user's input. These entities act as gateways into the knowledge graph. This process leverages a vector database. And then we go to entity text unit mapping. The system links the extracted text units to their corresponding entities. Discards the original text information as well during the process. Then we go for entity relationship extraction. This step extracts detailed information about entities and their respective relationships. Then we go for entity covariate mapping, and this step associates entities with their covariates, which can include statistical data or other relevant attributes. Then we go for entity community report mapping. This step incorporates community reports into the search results, adding some and also adding some global information. Then we go for utilization of conversation history. If available, the system leverages conversation history to better grasp the user's intent and context. And then the system constructs and responds to the user query based on the filtered and sorted data generated in the previous steps. The system generates a response to the query using the filtered and sorted data from the previous step. And that's all. Thank you, everybody, for your attention.